Hi, welcome to AV Video 6.2b Part 1, Additional Growth and Decay. So, they won't tell you this, but you should know that the rate of decay of radioactive materials is proportional to the amount present. That's simply known information. So, in the book, numbers 33 to 40, it says complete the table for the radioactive isotope. Number 38, it's carbon 14. They tell you the half-life is 5,715 years. They tell you that after 1,000 years, there's 1.6 grams. And the question is, find the initial quantity and find the quantity after 10,000 years. So we know it's exponential decay. We know that becomes y equals y0 times e to the kt. So I know that the half-life is 5715 years. So I replace t by 5715, and whatever I started with, after that much time, I have half of what I started with. Divide both sides by y0. Now, if you had a calculator, you could solve for k here, but what I'm going to do is that little trick where I'm going to replace this e to the kt by e to the 5715k to the power of t over 5715. Now, I know this quantity here is 0.5, and I have my function now, y in terms of t, although I don't know what the initial amount was, but that's what I'm going to be able to find out now, because they told me after 10,000, that there's 1.6 grams after 1,000 years. So if I replace t by 1,000 and replace y by 1.6, I will find out on my calculator, obviously, that the initial amount is 1.806 grams. So my actual function is this function right here, y in terms of t. And now we can answer the last question, find the quantity after 10,000 years. In other words, replace t by 10,000. And again, you'll need the calculator. You'll have 0.54 grams. Okay, 57 to 61, population in millions of a country in 2007, and the expected continuous annual rate of change k of the population are given. Find the exponential growth model P equals C times e to the kt for the population by letting t equals 0 correspond to the year 2000. Use the model to predict the population of the country in 2015. Discuss the relationship between the sign of K and the change in population. So in number 48, they give you Egypt. They tell you that the 2007 population was 80.3 million. They just write 80.3 because they told you it was in millions. And they actually give you the value of K here, okay? So we're going to use their version. You and I would write y equals y0 times e to the kt, but they're using p for population, and I don't know where they get c. Anyways, so we have that the population is 80.3, and it's in millions, so we'll just leave it as 80.3, and we know that that happens in 2007. So remember, if t equals 0 is 2000, then 2007 is t equals 7. So you end up you're able to solve the equation and find the value of C, which is the initial amount, and that is 71.29 million people. And now we can replace that C by 71.29, and we have our equation in P and T. So now they want to know what happens at t equals 15. Replace t by 15 and simplify. You'll get 92 million. And as you found out, because your k is positive, that means that the population is increasing. So sure enough, it started out at 80 million, and then by 2015, it's going to be 92 million. Okay, so they're all pretty well the same thing. Here's another. The number of bacteria in a certain culture is increasing according to the law of exponential growth. There are 125 bacteria after 2 hours and 350 bacteria after 4 hours. So two initial conditions. Find the initial population, which they're not giving us. Write an exponential growth model for the bacteria population, where T represents the time in hours. Use the model to determine the number of bacteria after 8 hours, and after how many hours will the bacteria count be 25,000. Okay, so we need a function in y and t so that we can replace t by 8 and find y, which is the number of bacteria. And here we'll be able to replace y by 25,000 bacteria and find out what the t is. Okay, so same deal as always. Y equals y0 times e to the kt. First initial condition, there's 125 bacteria after 2 hours. So I am able to isolate y0 here and get 25 divided by e to the 2k, which is e to the negative 2k. Then I have a second initial condition. So I'm going to take the same equation. This time I'm going to replace y by 350, and I'm going to replace t by 4. So now what I'm doing is I have this expression. And what I have this expression here, but I'm going to replace the y0 by 125 e to the negative 2k. So it ends up that e to the 2k is 14 over 15. Okay? Now, you can then take this equation here, and with the e to the 2k is 1415, and you'll be able to find that y0, you'll need a calculator for this, that y0 is about 45 bacteria initially, 44.64. So now we have our actual equation. We still have the k that we don't have, but now we know the final amount is the initial amount, which we figured out was 44.64 times e to the kt. But now over here, I know that e to the 2k is 14 over 5, so I'm going to replace e to the kt by e to the 2k to the t over 2. Notice when I multiply these exponents, I get kat. But now I'm able to replace e to the 2k by 14/5. So there's my function finally, y is a function of t, and then you can answer the last two questions. After 8 hours, how many bacteria are there? So you replace t by 8 and solve for y. In the other one, how long will it take for there to be 25,000 bacteria? So you replace y by 25,000 and solve for t. Of course, you'll need that calculator to do that. Okay, this would be them deciding that they're going to give you a growth and decay problem that's a little harder, okay? So this is called Newton's law of cooling, okay? The rate of change of the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. If you take a hot pie out of the oven and that pie is at 400 degrees and you put it on the kitchen counter, it's going to cool down, but it's not going to keep cooling down until it eventually freezes over because your room temperature is probably 70 degrees. So it'll go from 400 degrees. At first it'll slow down quickly and then it'll slow down slowly. So now what happens, instead of the temperature being proportional, the rate of change of the temperature being proportional to the temperature, it's proportional to the difference between the object's temperature and the surrounding medium, which is the room temperature. Okay, so now we have the rate of change of the temperature, y being the temperature, dy dt is proportional to k times the difference between the temperature of that pie and the room temperature. Now that capital T will be a given constant. Okay? This particular differential equation does not become this, okay, because the original differential equation is not the